Intensity pattern of capital N slits. Part A. Consider an arrangement of capital N slits with a distance d between adjacent slits. The slits emit coherently and in phase at wavelength lambda. Show that at a time t, the electric field at a distant point P is the sum E0 cosine kr minus omega t plus E0 cosine kr minus omega t plus phi, a phase phi, plus E0 cosine kr minus omega t plus 2 phi, etc. and E0 cosine kr minus omega t plus capital N minus 1 phi at the end, where E0 is the amplitude at P of the electric field due to an individual slit. Phi is equal to 2 pi d sine theta over lambda. Theta is the angle of the rays reaching P as measured from the perpendicular bisector of the slit arrangement. Capital R is the distance from P to the most distant slit. In this problem, assume that capital R is much larger than D. Okay, so we will only work on part A of this problem to start with. So we have capital N slits. They emit light coherently. We are looking at a distant point P from these slits, and these rays are coming at different from different slits, and for each pair of slits we have a path difference of d sine theta forming here, and that angle is this angle with our parallel ray approximation. So for each individual pair of slits, the path difference delta, is Rn plus 1 minus Rn between the n plus 1 slit and n slit is equal to d sine theta. As you can see here, d cosine theta, d sine theta. So the path difference divided by a wavelength is equal to the phase difference divided by 2 pi. So we find that the phase difference is 2 pi d sine theta over lambda is the phase difference. And so what we see is that the phase increases by phi as we go from one slit to the other, because we have 2 path differences, 3 path differences, etc. as we go from one slit to the other. So the phase difference increases by phi as we go from one slit to the adjacent slits. Okay, so we adopt the electric field components of light coming from different slits. For slit 1, we have E0 cosine k capital R minus omega t. This is the contribution from the first slit. From the second slit, we have E0 cosine kr minus omega t plus phi. Second slit, because we have a path difference between first and the second given by d sine theta. And the third slit, E0 cosine kr omega minus omega t plus 2 phi, etc. Third slit, and all the way up to E0 cosine kr minus omega t plus capital N minus 1 phi. Or we can write it this way. The electric field at point P is the sum n equals 0 to capital N minus 1 E0 cosine kr minus omega t plus n phi. So n takes values from 0. So for 0 we have the first slit. For 1 we have the second slit. 2 we have the third slit. And for capital N minus 1 we have the nth slit contribution. Second was 1 phi. Third was 2 phi. So capital nth is capital N minus 1 times phi. So this will be our electric field at point P. So basically we have shown the suggested result by calculating the contribution from each slit and adding them up. So this is a traveling electromagnetic wave. Therefore, the electric field can be written as E0 cosine kr minus omega t. But for rays coming from different slits, we have a phase difference due to the path difference that develops between them. And this can be written finally in this form of a summation from n equals 0 to capital N minus 1 E0 cosine kr minus omega t plus n phi.